Steinhauer here. Welcome back. We are beginning to talk now about the structure of matter. And as you probably learned in high school, in your chemistry class, or somewhere along the way, all matter is made up of atoms. And atoms themselves are composed of a nucleus, which contains protons and neutrons, and where almost all of the matter, the mass of the atom is located, and the electron cloud, which contains electrons, which is even bigger compared to the nucleus than this cartoon drawing suggests. So let's hear some nomenclature, think about some nomenclature from describing atoms. The atomic number of an atom is the number of protons in the nucleus. And this defines what element you are. So all hydrogen atoms, in fact, all hydrogen atoms have a single proton in the nucleus. That is what makes it a hydrogen atom. Any atom that has 2 protons in the nucleus is helium, 3 protons in the nucleus is lithium, 6 protons in the nucleus is carbon. And so a atom's atomic number is the number of protons in the nucleus. And in fact, if you go to a periodic table of the elements, this number is listed there for all of these elements. So for instance, here's hydrogen. This 1 in the hydrogen is the atomic number. It is the number of protons in the nucleus. Helium has 2, lithium has 3, carbon has 6, neon has 10, iron has 26. So you can look right at a periodic table and tell exactly how many protons are in the nucleus just by looking at the number on that periodic table. The atomic mass number is the total number of nucleons, protons and neutrons in the nucleus of an atom. And that is the number that is listed usually here for hydrogen. For instance, hydrogen 1, H tells you it's hydrogen, which means it has to have a single proton in the nucleus. The 1 means there's 1 total protons and protons and neutrons. So H1 is an example of a bare proton, right? There is a single proton and no neutrons. Helium 4 is another example. Helium has an atomic number of 2, which means it has 2 protons. Helium 4, therefore, must have 2 protons, and the other 2 must be neutrons. Carbon 12, atomic number of 6, total nucleons of 12. So 6 of those must be protons, and 6 of those must be neutrons. Now, all 3 of these, and it's true for most of the light elements, the natural occurring ones have the same number of protons as neutrons, but that stops being the case fairly quickly. And in fact, there are other isotopes, we'll get to that in a second, of these that have different number of neutrons in their nucleus. Now, molecules, just so you're aware, when you say things like H2O and CO2, we know that water's, the molecular structure is H2O. This 2 does not refer to this one up here. This is a number of hydrogen atoms in the H2O molecule. So it doesn't refer to the number of protons in the nucleus. And usually that's a subscript or a superscript to tell the difference between those 2. CO2, carbon dioxide, again, at 1 carbon atom and 2 oxygen atoms. Okay, I already mentioned this word before, but let's define it now. An isotope is an atom. Two atoms are isotopes if they share the same number of protons but different number of neutrons. For instance, helium-4 and helium-3. Both are helium and therefore have 2 protons in the nucleus, but helium-4 will have 4 total nucleons, so 2 neutrons, and helium-3 will have 3 total nucleons, of which one of those then has to be a neutron. Here are some other examples. Carbon 12, 13, and 14 are all isotopes of carbon. Carbon 12 is the most abundant, the most naturally occurring, but 13 and 14 are also stable elements. And the only way these differ is in the number of neutrons in the nucleus. These are all still carbon atoms, though, and behave very much identically. It is the charged particles. It is those protons that really affect the chemical and nuclear structure of the atom. And therefore, all of these behave almost identically. And so there isn't much of a difference chemically or nuclear physics-wise between these isotopes. And so they're all carbon, they all behave basically the same, but they do have different masses, for instance. Okay, so that's the nucleus of the atom. What about the electron clouds of the atoms? We know that most atoms are neutral, and since there are +1 charged protons in the nucleus, that means that for every proton in the nucleus, there must be a -1 charged electron in the electron cloud. So carbon atoms that are neutral with 6 protons also have 6 electrons. Hydrogen atoms with a single proton have a single electron. And the interesting thing about these electrons is that they are not, the electron cloud is not like, let's say, the solar system. Atoms, though, can be thought kind of like solar systems, right? You've got most of the mass in the center with the nucleus, whereas the sun is in the mass at the center of the solar system. You've got the electrons moving around in orbits, and you've got the planets moving around in orbits. The difference is, and there's several differences. One of the differences is that planets can orbit at any radius. There's nothing limiting where they physically orbit that nucleus, the sun. Electrons are confined and must orbit at very specific energy levels. There's only certain orbits that are allowed. And if you're interested in why, you can take a phys chem class or an upper level physics class to figure out why. There's really cool physics going on here. But for our purposes, it's enough to know that there are specific energy levels or specific orbital radii that these electrons can move in and not in others. So here is an example of the energy levels of a hydrogen atom. It's the simplest one to write down. And so it's usually, and hydrogen is the most common and abundant element in the universe. So it's very useful for those reasons. Here is the energy level diagram of a hydrogen atom. So this isn't showing you orbits, it's showing you energy levels. And the ground state, you can consider the lowest energy level. That is the orbit that would be closest to the nucleus. And then a second, level 2, level 3, level 4, level 5, and on up. And each atom has a unique set of energy levels. And electrons can only exist at these blue lines, and they cannot exist in the areas in between. And so if you have an electron sitting here at the ground state, if you excite it, if you bump it into another atom, or if you shine a light on it, it can be excited and can move from this ground state into one of these upper level states. The interesting thing is that each one of these electron states corresponds to a specific energy level. And so for hydrogen atoms, there's always the same energy difference between, let's say, the n=1 level and the n=2 level. And so since these correspond to a specific energy, it takes a specific energy of, let's say, light to make to be absorbed to make a atom electron move from the n=1 to the n=2 state. So again, if you have an atom and you have an electron, you can have it absorb some energy and have that electron move to a higher energy state. It's sort of like an energy storage system, right? You can move an electron to a higher energy state, and that energy will be stored, therefore, in that atom, and that atom will have a higher energy. That energy can be released if the electron falls back down to a lower energy state. And typically, this is done with photons. It's done with light. So a photon will come in. It will hit an electron that's at a low energy state. That electron will jump up to the atom will absorb that photon, and that energy will go into moving an electron from a low energy state to a high energy state. There's an energy principle, there's a physics principle called conservation of energy, which is important here, which is that energy can neither be created nor destroyed. So if a photon's coming along with some energy, and that atom absorbs that photon, that energy has to be contained within that atom. And that typically happens by exciting an electron to a higher energy state. Then that electron can jump back down, and what will happen? Well, a photon will be emitted with exactly the same energy as the difference between its higher state and its lower state that it jumped down to. And you can see listed here some wavelengths, right? Because we know now that a photon of a particular energy has a particular wavelength. And so there are wavelengths of light that are associated with each of these transitions. For instance, if an electron jumps from the n equals 2 state to the n equals 1 state, that will release a photon that has a specific energy. And that specific energy corresponds to a wavelength of 121.6 nanometers. If an electron jumps from the n equals 3 state to the n equals 1 state, that corresponds to a energy difference, which corresponds to a wavelength of 102.6 nanometers. Now, you'll see 121.6, 102.6. If you remember your electromagnetic spectrum, these are ultraviolet photons. These are not in the visible part of the spectrum. These over here are in the visible part of the spectrum. Here is the n equals 3 to n equals 2. This one is 656.3 nanometers. This is a beautifully red photon. Here is one from n equals 4 to n equals 2. This one's a slightly higher energy photon. This one looks very teal. 434, n equals 5 to n equals 2 gives you a very blue photon. And 410 is just at the very edge of the visible part of the spectrum, an indigo or violet photon. So it's interesting. The first 4 lines of this series are all in the visible part of the spectrum. And so these are some of the more important lines because they were discovered first, and they are the ones that are easiest to detect and see with the unaided eye. These actually have names. In fact, the n equals 3 to 2 transition, the 656, is called H alpha. The n equals 4 to 2 line, 486.1, is called H beta. And you can probably guess this is H gamma and H delta if you know your Greek alphabet. H for hydrogen, alpha for the first or lowest energy or longest wavelength line in that particular series. These have names and these have names too. I'm not going to get into those names, it's not that important. The important thing is what happens if a photon comes along of the right wavelength. An atom can absorb that photon and an electron will move to a higher energy level. That electron can then spontaneously move back down and that atom will emit a photon of a very specific energy and therefore a very specific wavelength of light. Here is another diagram showing those. And again, this is important. The in-between regions are not allowed, right? So if you have a wavelength, let's go back to this diagram. If you have an atom sitting here in the ground state and a photon comes along that doesn't have 121.6, maybe it has 122 or 123 or 119 nanometers, that photon cannot be absorbed by this atom because there is no available energy state there for that electron to go to. So the only states that are allowed are these particular energy levels around the atom. And so it's not possible to absorb or emit a photon of a wavelength that's not one of these differences between energy states in the atom. It's not allowed to go halfway. You can't do that. You have to begin and end always, whether you're emitting a photon or absorbing a photon, at one of these allowed energy states. It's also possible, this is allowed too, for an electron to leave the atom entirely. In fact, there is a particular energy level above which there are no bound states anymore, right? This is the electron being completely freed from the atom altogether. And so that's also possible. It's possible to have a high enough energy photon that it goes completely off of the atom altogether and we call this an ionization. Anytime an ion is any charged particle, and once an electron leaves an atom, you are left with a net positive charge on that atom, and so it becomes an ion, and so we call this the ionization, an ionization reaction. Okay, that is the basic structure of atoms and how it's important for the structure of matter. We'll talk in the next video about how light and matter interact and how you can interpret different spectra to have come from different states of matter. So look forward to that. See you next time.